is, how confident are you that a single type of intervention, this epigenetic reprogramming, will be sufficient to deal with all the downstream hallmarks of aging? And this is kind of opposed to other approaches to rejuvenation, which seem to suggest that multiple separate interventions will be necessary on a regular basis.
Right. Well, I'm not certain that reprogramming is the only thing we need. We're going to need senolytics, perhaps some telomerase activators. There are a lot of other things that could help get us beyond 120 maximum. That said, this reprogramming discovery is so fundamental. It's as though we've discovered something that we weren't even expecting. It truly will be a paradigm shift. What we've published, and I wrote in the book, is that Horvath found the clock. So imagine we have a clock on the wall, and we think that the clock just is an indicator of time. What our new results suggest is that that clock is actually controlling time. And when we move the hands backwards, we actually get to rewind back youth, and that we have a backup copy of our epigenome that we can access using Yamanaka factors, which you'll read about probably in another few pages. Why is that important? Well, when we've treated mice, we see all of the hallmarks of aging go backwards and forwards, by the way. We can also epigenetically age mice, and we give them aging. And so it's possible that, and what I propose in my book and in things that I'm writing now, is that this epigenetic theory, this information theory of aging, can explain all of the hallmarks. And if that's true, then by addressing the epigenome, these other hallmarks may by and large go away. And that's what we're actually seeing in mice now by restoring vision in old mice. And if we can restore vision in old mice, it's exciting to think what else we might be able to reprogram. But I don't know if it's perfect. It's early days. And I still think it's worth pushing ahead very hard with these other approaches addressing the hallmarks individually as well.
First of all, it's important to know that our lifespan and our health in old age, only 20% of that we inherit from our parents. The rest is mainly up to how we live our lives. But if you smoke, you can have the clock accelerate. And if you eat well, if you eat less often, if you exercise, you can slow that clock. So what is that clock? It's called the epigenetic clock. And it's actually, the epigenome is the key word here. So let me explain briefly. There are two types of information in the body. One is genetic, the information we get from our parents. But the other type of information that is equally important is what's called the epigenetic component. And that can change with how we live our lives. And the epigenome, just to summarize, is how the cell reads the DNA. So a cell that's in your brain has to use a particular type of epigenome to stay a nerve cell, and a skin cell uses a different epigenome. And it's the loss of that epigenomic information that I believe is the main driver of the aging process. In other words, aging is just simply a loss of information over time. We know of one particular chemical mark that gets changed over time, and that's what we call the epigenetic clock. That's the DNA methylation. So methylation is just a little chemical that sticks to the letter C in our genome. And we can read that with a little machine about the size of a candy bar. And that's how we read the clock. Those little methyl groups change in our bodies over time, and we just read them. But that's not the only thing that changes with time. The epigenome, as you said, involves proteins that loop DNA or bundle it up very tightly like a spool or a hose on a driveway so that those genes stay off. And we're just learning how to fully understand how that structure is behaving over time during aging. But those DNA methyl marks are a very good clock. Now, one of the biggest discoveries that's happened over the last 12 months, and I was very fortunate that my PhD student was one of the people who helped discover this, is that those DNA methylation marks, when we wind back aging, and we, as I mentioned, we have a way of doing that now, those DNA methylation marks, you have to remove them for the age of the cell to go back and for the cell to behave as though it's young again. So in other words, the clock isn't just measuring time on the wall, it's actually part of time itself. So for the last 15 years, we think we've figured out one of the main drivers of the clock advancing, and it's broken DNA. So every time you go out and you get a bad suntan, or you get an X-ray, you're breaking chromosomes. And the act of having to stick those chromosomal ends back together, the DNA molecule, the double helix, it has to open up the chromatin, as we call it, the epigenome has to rearrange. And then the cell has to repack all of those structures back together. And it doesn't do it perfectly. So every time you get a broken DNA molecule in your cell, and that happens in our body about 20 trillion times every day, totally, that advances the clock by a little bit. And over time, over decades, these DNA breaks will accelerate aging. And we have good evidence for this. And one of the bits of evidence is that if we break the chromosome in a mouse, and we do that for a few weeks, that mouse will go on to age 50% faster than the brothers and sisters that didn't have that treatment.